Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Good morning and greeting to all of us. Thank you for the committee for giving time to me, and now we would like to present the result of our research about one topic in combinatorial research. The title is Irregular Reflexive Labeling of Palm tree graph C3b2R and C3b3R. Before I show the result of research that we have done, allow us to introduce ourselves. Okay, me, the first author, Rakel Junetty, and two other authors, namely Indriati and Winarno, from Combinatorial Mathematics Research Group in Department Mathematics, Faculty of Mathematics and Natural Sciences, Universitas Sebelas Maret, Surakarta, Indonesia, conducted in 23 until 24 August 2021 at the event I-CMME International Conference Mathematics and Mathematics Education. You can see the slide, it is introduction. Based on Wallis and Marr research in 2013, the mapping of the element of a graph to positive integer is called labeling a graph. And based on Gallian research in 2007, Gallian divided graph labeling into three types. Number 1, vertex labeling. Number 2, edge labeling. And number 3, vertex and edge labeling. It can call total labeling. And based on Bacha research in 2007, total k-labeling divided into two types. There are a vertex irregular total k-labeling and an edge irregular total k-labeling. Called an edge total irregular k-labeling because total k-labeling with all edges have different weights. The formula can write WTXY equal Fx plus Fxy plus Fy. Based on Bacha research in 2017, an edge irregular reflexive k-labeling is defined as the function Fv with Vg mapped to 0 to 4 until 2 kV and Fi with Ig mapped to 1, 2, 3 until Ka, where K equal makes Ka to Kv. And now we know the minimum K, which F is an edge irregular reflexive k-labeling, is mentioned as reflexive edge strength of graph G, symbolized by G. Ryan proved by them for every graph G, G greater than ceiling of cardinality of S per 3 for cardinality of S not equivalent to and 3 in modulo 6 and ceiling of cardinality of S per 3 plus 1 for cardinality of S or size equivalent to 2 and 3 in modulo 6. Many research can have been proven rest of some graph. For example, based on Indriati research in 2020, proof G corona of a path and complete graph K1 and also corona of a path and path 2. Now, main results. What does palm tree graph mean? Okay, based on Ahmad paper in 1997, the palm tree graph CPBQR is a graph obtained a graph broom BQR and cycle CP from by joining a path that connect the end of vertices the broom graph with one of vertices of cycle. Okay, we know the palm tree graph CPBQR consists by set of vertices V, C, P, B, Q, R equal W0 union W, H, which H greater than 1, less than R, union Xi, which I greater than 1, less than Q, union Yj, which J greater than 1, less than P, and set of H, I, C, P, B, Q, R equal W0, WH, which H greater than 1, less than R, union W0, X1, union Xi, xi plus 1, which I greater than 1 less than q union xp y1, which p greater than 2 union yj plus 1, which j greater than 1 less than p union yj plus 2, which j greater than 1 less than p. Choose. Palm tree graph has r plus q plus p plus 1 vertices and r plus q plus p plus 1 axis. Consequently, the palm tree graph C3b2r has r plus 6 vertices and r plus 6 axes. Then the palm tree graph C3b3r has r plus 7 vertices and r plus 7 axes. So the reflexive edge strength or rest G of palm tree graph C3b2r can be found by using theorem 1, and the reflexive edge strength or rest G of palm tree graph C3b3r can be found by using theorem 2. Based on Augustine result in 2020, there are particular cases where we will use direct proof to prove theorem of our results. Theorem 1. For every natural number p, q, r with p equal 3, q equal 2, and r greater than 3, in point A, for r greater than 3 less than 11, the formula of the rest C3b2r equal selling of r plus 6 per 3 for r not equivalent to 2 and 3 in modulo 6, and shelling of r plus 6 per 3 plus 1 for r equivalent to 2 and 3 in modulo 6. And in point B, for r greater than 12, the formula of rest C3b2r equal shelling of r per 2 for r not equivalent 3 in modulo 4, and shelling of r per 2 plus 1 for r equivalent to 3 in modulo 4. Okay, now we prove theorem 1. In point A, first we prove the lower bound of rest C3b2r for r greater than 3 less than 11. According to the definition, the edge of the palm tree graph C3b2r has r plus 6. From the lemma 1, the results obtained are as follows. The formula rest G equal K, selling of r plus 6 per 3 for r plus 6 not equivalent to 2 and 3 in modulo 6, and selling of r plus 6 per 3 plus 1 for r plus 6 equivalent to 2 and 3 in modulo 6. This statement equivalent to rest C3b2r greater than selling of r plus 6 per 3 for r not equivalent to and 3 in modulo 6, and selling of r plus 6 per 3 plus 1 for r equivalent to and 3 in modulo 6. At the second time, we prove the lower bound of rest C3b2r for r greater than 12. The maximum degree of C3b2r is r plus 1. Based on Augustine result, if 6q less r with the result that q less r per 6, therefore from proof of theorem 1, in point B we get rest G equal K greater than selling r per 2 for r minus 1 not equivalent to 2 in modulo 4, and selling of r per 2 plus 1 for r minus 1 equivalent in 2 modulo 4. This statement equivalent to rest C3b2r greater than selling of r per 2 for r not equivalent 3 in modulo 4, and r per 2 plus 1 for r equivalent to 3 in modulo 4. Next, we construct K-labeling F with K to prove upper bound in irregular reflexive labeling of C3b2r. Okay, you can see the label of the formula of label of vertex and label of edge the following sets. the label of vertex and label of edge, we get the label of maximum vertices and edges of the lower bound and the upper bound, and the label of all vertices are even. In this slide, you can see the weight of edge from graph C3b to R like this. The proof rest C3b to R is completed. Figure 1 evidence the illustration of an irregular reflexive labeling C3b25 and the labels and names of the vertices and edges indicated by black color and the edge weight indicated by green color. Okay, like this. So if you want to make it easier for your understanding, one of them you can apply a formula that has been obtained in a graph like on a slide. Next, we will discuss about column graph 3, C3b3r. Theorem 2. For every natural number p, q, r with p equal 3, q equal 3 and r greater than 3, point 1 for r greater than 3 less than 11, the formula rests C3b3r equal selling of r plus 7 per 3 for r not equivalent 1 and 2 in modulo 6 and selling of r plus 7 per 3 plus 1 for r equivalent 1 and 2 in modulo 6. Point B, for r greater than 12, the formula of rest C3b3r equal selling of r per 2 for r not equivalent 3 in modulo 4 and selling of r per 2 plus 1 for r equivalent 3 in modulo 4. We prove theorem 2. In point A, first we prove the lower bound of column 3 graph is rest C3b3r for r greater than 3 less than 11. According to the definition, the edges of the column 3 graph C3b3r are r plus 7. From lemma 1, the result obtained are as follows. The formula rest G equal k greater than selling of r plus 7 per 3 for r plus 7 not equivalent 2 and 3 in modulo 6, and then selling of r plus 7 per 3 plus 1 for r plus 7 equivalent to 2 and 3 in modulo 6. This statement equivalent to rest C3b3r greater than selling of r plus 7 per 3 for r not equivalent 1 and 2 in modulo 6, and then selling of r plus 7 per 3 plus 1 for r equivalent to 1 and 2 in modulo 6. At the second times, we prove the lower bound of rest C3b3r for r greater than 12. The maximum degree of C3b3r is r plus 1. Based on Augustine research, if for q less r with the result that q less r per 4, it means that r is much larger than q. Choose maximum of r plus 1 per 2 plus m and selling of r plus q plus 4 per 3 plus n, where m equal 1 for r minus 1 equivalent to 2 in modulo 4. Therefore, from proof of theorem 2 in point B, we get formula rest G equal k greater than selling of r per 2 for r minus 1 not equivalent 2 in modulo 4, and then selling of r per 2 plus 1 for r minus 1 equivalent to 2 in modulo 4. This statement equivalent to rest C3b3r greater than selling of r per 2 for r not equivalent 3 in modulo 4, and then selling of r per 2 plus 1 for r equivalent 3 in modulo 4. Next, we contract K labeling F with K to prove upper bound in its irregular reflexive labeling of C3b3r. Okay, in this slide you can see the formula of the label of vertices and label of edges of column 3 graph C3 of edges. We get the label of maximum vertices and maximum of edges of the lower bound and the label of all vertices are even, and you can see the formula of the which of each like this on a slide. So the proof of res C3B3R is completed. Figure 2 evidence the illustration of an irregular reflexive labeling on C3B37. The labels and the names of vertices and edge indicated by black color and the edge weight indicated by green color. So if you want to make it easier for your understanding, you can use the formula has been obtained in a graph like on a slide. And furthermore, we have open problem for the direction of the next research, and we are still in progress. An open problem determine of reflexive strength of palm tree graph CPBQR for P greater than 4 and Q greater than 4. It is reference that I can use to make my paper, and sorry if there is a wrong word, and if you have any question, you can directly ask through the form provided by the committee, and inshallah I will try to answer your question. And thanks for your attention. Wassalamualaikum warahmatullahi wabarakatuh.